In the last video, I gave the mathematical definition of a derivative. This definition is fine for symbolic mathematics, but a direct numerical calculation results in undefined operations. So, in this video, we'll see how to calculate a numerical approximation to a derivative. This is the definition of a derivative. The derivative, denoted by dx of the function, is the slope of a straight line in the limit as the distance between the points becomes infinitesimally small. Letting delta x go to 0 is allowable in symbolic math, as long as there are no sudden changes in the value of the function. However, if we directly try to substitute a value of 0 for delta x in this equation, both the denominator and the numerator become 0. Since numerical analysis is all about using numbers, this definition of a derivative is fairly useless to us. We'll get around that problem by just understanding that we usually don't need the exact solution to an equation. Our solution just has to be close enough to the correct answer. Numerically, we can calculate the derivative of a function by using the mathematical definition, but just substitute a small but non-zero value for delta x into this function and hope that it gives us meaningful results. So the equation we'll use for a derivative is df by dx is approximately equal to f of x plus delta x minus f of x over delta x. Then we'll choose an arbitrary but small value for delta x and hope this gives us a derivative that's close to the actual value. But how do we choose a value for delta x? It needs to be small, but not so small that we get significant round-off errors. There are two fundamental cases in which we may want to perform a differentiation. The first is probably obvious. We're given a symbolic functional relationship for f of x, and we need to differentiate it. The second is probably less familiar. We have a set of measured data points for which we don't have the underlying functional relationship. In numerical analysis, our approach to solving these two cases is basically the same. Either way, we're going to be using numbers. If we're given a functional relationship, we can evaluate the function to determine the values we need in our approximation of a derivative. If we're given a set of discrete data points, we already have the values to plug into the equation for the derivative. The only difference is that if we have a functional relationship, we can generate the numbers that we need for any arbitrary value of delta x. Now I'll talk about calculating the derivative of a functional relationship. The steps I'll provide here are a relatively common approach, but not necessarily universal. First, of course, you'll need to know the value of the independent variable x at which the derivative is to be calculated. We also need a first guess at a value for delta x. After x and delta x are known, we can estimate the derivative. Just plug the correct numbers into this equation. Now the problem's to know whether we're close to the correct value or not. Typically, we do this by reducing delta x, for example, dividing the original value by 2, and recalculating the estimate of the derivative using the equation from step 3. Compare the result you got with the original estimate to see if reducing the delta x had an effect. If the estimate doesn't change, then you've probably got a pretty good estimate for the derivative. However, if you get what you consider to be a significant change in the estimate by reducing delta x, try reducing it again and checking to see if the estimate continues to change. Keep reducing delta x until it no longer has a significant effect on the derivative estimate. Now I'll do a demonstration to illustrate this process. I'm going to take the derivative of a MATLAB function called humps in this demonstration. But before I do that, let's plot it and see what it looks like. First, I'll set up a vector of x values. To calculate the values of the function, I'll set y equal humps of x. Now I'll plot the function. I'm going to estimate the derivative of the function where x is 0.4. I'll put a black circle at that point. The derivative of the function at this point will be the slope of a line that's tangent to the curve at that point. Now I'll set the value of the point where I want to calculate the derivative. I also need a value for delta x. I'll start with a fairly high value of 0.1. Now I'll calculate the derivative of the function at that point. Deriv equals the value of the Hump's function at x plus dx minus the value of the Hump's function at x. This difference in the function value is divided by dx, which is the difference in the values of the independent variable. This value of delta x gives an estimate of the derivative as about negative 284. We don't really know whether this is correct or not though, so let's reduce the delta x by a factor of 10. When I redo the calculation, I get a value for the derivative of about negative 463. This is a huge difference, so I'd better reduce the step size again. I'll try 0.001. Redoing the calculation again gives about negative 485 for the derivative. This is around a 5% difference, which still seems like a pretty big change, so I'll reduce the delta x by another factor of 10. This gives about negative 488, which is pretty close to the value with dx equals 0.001. Still, let's reduce delta x one more time to make sure. This gives about negative 488 again, so it looks like I've converged on a consistent solution. Just for fun, I'll plot the derivative on the figure showing the Hump's function. I'll set up a new set of x points in the region of x equals 0.4. So, my x points for the slope start at 0.3, increment by 0.1 to 0.5. I can use a large increment because this is a straight line. Now calculate the line passing through x equals 0.4 and with a slope given by the derivative that I calculated. So it's going to be the value of the Hump's function at x plus the derivative, which is the slope, times the x values in slope underscore x minus the x value 0.4. Now I'll plot this line on the previous figure. The red dashed line looks like a good approximation to the slope of the tangent to the curve at x equals 0.4, so our last estimate of the derivative seems reasonable. For the case in which we only have a set of given data points to represent the function, the option of modifying delta x to determine whether the estimate is consistent doesn't exist. In this case, we simply have arrays of numbers. My vector x contains n values of the independent variable, and the vector f contains n values of the function at the corresponding values of x. So f1 is the value of the function at x1, and so on. To calculate the derivative at x sub I, first choose delta at x sub I to be the difference between x sub I plus 1 and x sub I. Then the derivative at this value of x is just f sub I plus 1 minus f sub I divided by that delta x. There are some issues associated with this approach if these arrays are generated from measured data. Measured data always have errors and noise, and taking the derivative of measured data usually causes problems. In order to see some effects of differentiating measured data, let's measure the position of a spring mass damper system. Then I'll differentiate the position data to get velocity. This is our system. It's a slinky with a platform on the bottom of it. This system can store energy in two ways. Stretching the spring stores potential energy in the slinky, and the velocity of the platform stores kinetic energy in the mass. So to completely describe this system, I need to measure both the velocity and the position of this platform. I don't have a way to measure its velocity, but I can measure its position with this acoustic proximity sensor. This sensor emits an ultrasonic signal which bounces off the platform and returns. The travel time round trip is converted to a voltage, which I'm recording using a USB-based oscilloscope, which is then recorded onto the hard drive of my computer. Once it's there, I can differentiate the position information to get the velocity, and I'll have completely characterized the system's response. So I'm going to displace this and release it and record the position as a function of time. Before I differentiate the measured data, I'll take the derivative of a function that I'll evaluate in MATLAB. This will give us a chance to see what we should expect for a similar function that doesn't have noise or errors in it. I'll set up the function for values of time from 0 to 5 seconds at intervals of 0.01. I'll create a variable named y, which is e to the negative t times the sine of 2 times pi times t. I'm going to calculate the derivative for all values of x. I'll do this with a for loop first. I'll put the code in a script file named deriv_demo. First, find the number of points in the vectors representing the function. Now we'll loop through the first n-1 points. Since we have to use 2 points to calculate every derivative, we won't have an estimated derivative for our last data point. So for k equals 1 to n-1. I'll save the derivatives in an array so that I can plot them later as a function of time. Deriv of k equals the difference between y at k plus 1 and y of k divided by the difference in time between k plus 1 and k. Now I'll plot the function and its derivative together. The vertical scales on the two functions will be very different, so I'll use the plot yy command, which uses and displays different scales for each line. Plot yy, first plot the original data, t, y, then the first n-1 time points, and deriv. Notice that the value of the derivative is high where the slope of the original function is high, and it's 0 where the slope of the original line is 0. So the derivative is 0 at the maximum and minimum values of the function. Now let's try taking the derivative of the data we acquired in the demonstration. We were measuring the position of the bottom of a spring mass system, which gave us the energy in the spring, but we need the velocity in order to get the energy stored in the mass. First, I'll load the data. Load smd.txt space dash ASCII, since this is ASCII data. For this example, I'm going to use a MATLAB function called diff to calculate the derivative. Diff takes the difference between successive elements in an array. It returns an array containing these differences. So the derivative will be the differences between the positions, which is the second column of the array of data, divided by the differences in time, which is the first column of the data. So deriv is equal to diff of smd, all the rows, second column, dot slash, I need an array operation here, diff of smd of colon, comma, 1 for the first column of the array. Now I'll plot the derivative along with the original data. The derivative is the red line, which is really jagged and almost useless as an indicator of the velocity of the mass. The problem is the noise in the original data. If we zoom in on the data a bit, we can see that the data has different discrete levels connected by almost vertical lines. This is because of the digital nature of the sensor I used. The sensor only outputs certain discrete levels, which are determined by the number of bits available to represent the data. So the derivative is very high when we switch from one level to another, and almost 0 between the level changes. This doesn't reflect the behavior of the actual motion of the platform, so we don't get a useful representation of the velocity of the mass. In general, taking the derivative of measured data is a bad thing to do.
Finally, I'll summarize a couple of MATLAB commands that can be useful when taking derivatives. As I mentioned in the video on curve fitting using polynomial-related commands, there is a command called polydir which returns the derivative of a polynomial. The derivative of a polynomial will be another polynomial. So you send this command the coefficients of the polynomial you want to differentiate, and you get back the coefficients of the derivative of that polynomial. This command isn't, strictly speaking, a numerical analysis technique. It's actually performing a symbolic type analysis to give an equation for the derivative. A command that's more directly related to the material for this course is the diff function, which I used in the previous demonstration. It takes differences between successive elements in an array.
This concludes my discussion of numerical differentiation. It turns out that numerical differentiation isn't all that useful for engineers, primarily because of the issues associated with noise and uncertainty that we saw when we differentiated the Slinky system data. However, the concept of differentiation is the foundation of another technique that's extremely important and useful: numerical integration. Integration is the topic of the next chapter.